Hey, welcome back. This is going to be the last page of notes for week 1 of our distance learning. So previously we talked about greatest common factors, using the area model or the box method to factor trinomials. And now we're going to look at some specific polynomials that have this very unique pattern or structure that if you recognize it, makes them very easy to factor. If not, I mean, you can always fall back and do the use the box method on these. All right, so these notes have a starter, which is kind of like a warm-up. So you should pause the video, try problems 1 and 2, and then unpause when you're ready to check your answer. Okay. All right, so the directions say find the product, which is in math means to multiply. Okay, and the way that we multiply polynomials is using the box method. Right? So we're going to have the terms x and -3, x and +3, and then just do 4 rounds of multiplication. Okay, x and x makes a product of x squared. This is going to be a product of 3x. That's going to be -3x, and the last product is -9. Okay. All right. Recall that the 2 terms on the diagonal are the only like terms in the box, and so we would combine them. But in this case, they're opposites. And opposites always add up to 0. Okay. So the product, or the result that you get when you multiply these 2 polynomials, is you just get x squared and -9. All right, let's look at problem number 2. Realize I should probably zoom in some here. Okay. All right, so we're going to set up the box method once again. 2x plus 5y, 2x minus 5y. And then it's going to be 4 rounds of multiplication. Okay, 2x times 2x is 4x squared. Okay, 2x times -5y. So let's see, the coefficient will be -10, and the term is going to have a power of x and a power of y in it. Okay, this product here will be +10 xy. And then our final product, 5 times -5, that's -25. Y times y, that's going to give us a second power of y squared. Okay. Now, once again, we're going to look for like terms. Okay. And they always tend to show up on this diagonal here. Right. So both of these terms have 1 power of x and 1 power of y in them. But when we look at the coefficients, they're opposites. Okay. That means they're just going to cancel each other out. Okay. So the result of multiplying these 2 binomials, well, we're going to get a 4x squared term. Okay, these 2 terms cancel out, add up to 0, and we're going to get a -25y squared term. Okie dokie. All right, so factoring difference of squares is going to take advantage of this particular pattern where the like terms cancel out, right? And if you look at the 2 answers we got, right, every coefficient here is a perfect square, right? This is a 1, which is 1 squared. This is a 9, which is 3 squared. 4 is a 2 squared. 25 is 5 squared. So if you notice that you have a polynomial that contains only perfect squares as coefficients, chances are that it will be able to factor into binomials that have the same coefficients in their terms, right? 2 and 2, 5 and 5, 1 and 1, 3 and 3. Okay, so let's read through this. Difference of squares is a shortcut that can be used to factor an expression of the form x squared minus y squared, right? If you notice that the first term and the last term are perfect squares, either the variable is a power that's a perfect square or the coefficient is a number that's a perfect square, you can use this shortcut. Okay. In this general case, the factored expression is going to be x plus y, x minus y. Okay. Note, the GCF may be used before using the difference of squares. Another note, this technique does not work with a sum of squares. It only works when there's a minus sign between the terms, right? Look at our answers here. Minus sign, minus sign. Okay, it wouldn't work if there was a plus sign. All right, so there's some examples that are already done. X squared minus 25. So if you think about it, x squared is the product of x and x. And 25 is a perfect square. It's the product of 5 and 5. Okay, and so you can see the factors contain x's as their first term and 5's as their second term. It's just that one of those 5's has to be negative since the term was a negative 25. Okay, and you can see in the next one, x squared is the product of x and x, 9 is the product of 3 and 3, and the factors contain x's and 3's. Okay. This last example has a GCF, right? So they divide the 3 out first, and then what you're left with is x squared, which is the product of x and x, 25, which is the product of 5 and 5, and then you've got your factors that contain x's and 5's in them. Okay. So this type of factoring is really more of like pattern recognition, right? Recognizing the patterns and being able to utilize the pattern of the structure. Okay. Now, as a fallback, you can always use the box method. Okay. So I'm going to go ahead and show the box method on these 6 problems, but you can also just use the shortcut that you've seen here. Okay. All right. So example 1a, x squared minus 64. Okay, so if I had no clue what to do, but I knew how to use the box method, all right, I'd put x squared there and negative 64 there, and then I'd write my 2 clues. Now, there's only 2 terms here, right? So I could think of there being a 0x term, right? X squared plus 0x minus 64. Okay, and so that gives me my first clue, is that my 2 empty boxes here have to add up to 0x, and then the other clue is that they have to multiply to negative 64x squared. Okay, and so you probably will realize pretty quickly that the missing terms are positive 8x and negative 8x. Okay, they have to be opposites. That's the only way to add up to 0. Okay. All right, so we know we're going to have factors of x outside the x squared box. We'll have a factor of negative 8 there and positive 8 there. Okay, so x plus 8 and x minus 8 are the factors. Okay, now remember, you don't have to use the box method, right? This is just a fallback, a backup, right? What you should be doing is trying to recognize the pattern. X squared is the product of x times x, and negative 64 is the product of 8 and negative 8. Okay. All right, B. Okay, so already I like that 16 and 9 are both perfect squares. Okay. All right, let's try the box method. I've never done one like these with the box method, right? It has 2 variables. Okay, 16h squared, negative 9a squared. We could think of the middle term just being 0, right? There is no middle term there. All right, so we know that the 2 missing terms have to add up to 0 and has to multiply to make, oh geez, I can see why you wouldn't really want to do the box method now. What's 16 times 9? I'm doing this off screen. It's going to be negative 144 h squared a squared. Okay, that's awful. Well, because this is a negative 144, right, it becomes pretty clear to me that one of these has to be a positive 12 and the other has to be a negative 12. Okay, they each probably need to contain a power of h and a power of a. Okay. All right, so because this was a perfect square, I, probably could have just from the get-go realized that this is going to be 4h times 4h, and since that was a perfect square, probably should have realized that it was going to be 3a times negative 3a. Right. And you can see that 4 times 3 is 12, 4 times negative 3 is negative 12. Right, so everything fits out, works out. All right, so 4h minus 3a and 4h plus 3a. Okay, so that example demonstrates to me that, this box method is probably not going to be efficient, right? We probably don't want to use the box method. Okay. All right, so let's go on to C. Okay, and let's try using the shortcut now. Okay, so 121 is 11 times 11, 4b squared. Well, that's just 2b times 2b. Okay. So my factors should both begin with 11s, should both end with a 2b, but the pattern, remember we're trying to utilize pattern here, is that one factor will be a sum and the other factor will be a difference. Okay. How could you check your answer? The box method, right? Multiply that back together using the box method, right? Just like what we did in the starter problems, right? You multiplied to get this, right? So what we're doing here is we're just doing these starter problems in reverse, right? We're starting with a difference of squares and trying to figure out what were the two polynomials that were multiplied. Okay, so we're on D now, and you should realize that neither one of these numbers are perfect squares, right? 27 and 3 are not perfect squares. And so there was a note there that some may take more than one step. And remember that it mentioned something about the GCF earlier. Okay. So this polynomial, sorry, I'm so zoomed in I keep losing my place. This polynomial has a greatest common factor, right? And I'll just do it in one shot. Both coefficients are divisible by 3, and both terms have at least one power of g. Right, so we'll divide now. We're going to have 9g squared and minus 1. Okay. And so now I see that, hey, this is just, 3g times 3g. This is just 1 times 1. Okay, so we're going to have, well, 3g was our GCF. And then for our binomial factors, they'll both start with a 3g. They'll both end with a 1. One factor will be a sum, and the other factor will be a difference. Okay. All right. Problem E is, well, I thought it was simple, but I didn't realize that was a fourth power. All right. So what two powers multiply to make a fourth power? Well, it's a second power and a second power, right? B squared times b squared makes b to the fourth, right? And 16 is 4 times 4. Okay. And so now we know what terms go in the factors. Each factor will start with a second degree b, and each factor will end with a 4. One factor will be a sum, and one factor will be a difference. Okay, and it looks like we're going to do that again in F. Okay, x to the fourth is second power times the second power. 81 is just 9 times 9. Okay, so our factors will each begin with an x squared term and each end with a constant of 9. One will be a sum, the other will be a difference. All right, so I'm going to invite you now. We did 3 problems. So you really don't want to use the box method, right? It's going to be a lot of work, and sometimes if you're like in number B, you've got 16 and 9 multiply to make a 3-digit number. You've got 2 different variables. It gets pretty complicated rather quickly. So you really want to be looking for the pattern and the structure. Okay. So I encourage you now to pause the video, try these 4 problems on the second page, and then unpause when you're ready to check your answer with me. Okay, so let's look at number 1. This is perhaps the simplest of the 4. X squared is the product of x and x. 25 is the product of 5 and 5. So the factors will each begin with an x end with a 5. One is a sum, one is a difference. All right. Problem number 2. Okay, so you want to always check to make sure that what you're starting with are perfect squares. Okay, 4 is a perfect square, 81 is a perfect square. Okay, so 4x squared is going to be 2x times 2x. 81 is 9 times 9. So our factors will begin with a 2x, end with a 9, a sum and a difference. Okay. Number 3. All right, we've got a 4th power, which remember from our examples, that's a second power times a second power. So that's n squared times n squared. Okay, and then 25 is 5 times 5. Okay. So we're going to have an n squared in each factor, a 5 in each factor, one will be a sum, and one will be a difference. Okay. All right, and then our final one, 5y squared and 45. Now, neither one of those numbers are perfect squares. Okay. So what we're going to do here is factor out a GCF, okay, which is 5. So we're going to have y squared minus 9. Okay. All right, let's change colors. So y squared is y times y. 9 is 3 times 3. So we have that blue 5, right? That's our GCF. But following that are going to be our binomial factors. And each one will begin with a y, end with a 3. One's a sum, one's a difference. Now I just thought of something. If we go back to the first page, you know, I just realized that for e, so we factored this, we got b squared plus 4, b squared minus 4. I just realized that this is another difference of squares, right? B squared is b times b, 4 is 2 times 2. So we could have taken that a step further and written it as b squared plus 4, and then using a different color here, we would have b and b, 2 and 2, one sum, one difference. So we could actually write that as the product of 3 factors instead of just 2. Okay. Now, how come we can't do it with this term, or with this factor? Well, I think we had that somewhere in the notes, right? This technique does not work with a sum of squares, right? So this has a sum. We couldn't use this pattern to factor that. This one has a difference, it's a minus, and both of these terms are squares, so we could do it. Okay. And so on f, we could as well factor this some more, right? X squared is x times x, 9 is 3 times 3. And so this is a sum of squares, so can't do anything about that. But then this is a difference of squares, and using the pattern, we would get x plus 3 and x minus 3. All right, so thumbs up if you recognize that before I went back to it, because that's pretty good. You know, good on you if you notice that we could factor that even more. Okay, and I apologize that I missed that at first.